welcome to Data 100 Discussion 13, the last discussion of the semester. Congrats on making it this far. So my name is Jake, and today I'm going to be going over the first two PCA questions of this worksheet. And let's go ahead and start thinking about PCA, and this question really gives some good intuition as to what PCA is all about. And so question 1 says, PCA is one of the most popular dimensionality reduction techniques. It's relatively easy to compute, and the output is interpretable. And so just to kind of briefly go over why we're interested in PCA. So PCA is a way of taking generally a data set where D, the number of features, is extremely large, and reducing the dimensionality of that data set, say from D dimensions to K dimensions, where K is a lot smaller than D, while still preserving the important information in the original data set. So PCA is it can be used in an unsupervised setting where you don't have labels to just understand the data you're given better. And it can also be used in a setting where maybe you want to do some modeling, say with linear or logistic regression, like we've learned in this class, or decision trees, random forests, but our data set is really high dimensional, and we need to reduce the data set before we can do those modeling steps. So that's kind of the motivation behind PCA. And this question is going to use a surfboard, which you'll also see in homework 8, to build some good intuition about what PCA is all about. And so basically the idea of this question is we're going to think about applying PCA to this surfboard here. And I've plotted this 3-dimensional surfboard right here. You can imagine this is maybe the better representation than this 2D surfboard on the page here. But you can see all 3 dimensions here. And part A is asking us, given this original data, so remember, this is our original 3-dimensional data. You can see that we have 3 features here, X, Y, and Z, corresponding to the dimensions of the surfboard. So A is saying, given this data on the surfboard, and given this data here, what would the first 3 principal components be? And our choices are how far in inches along the board's length, so really just length, width, and thickness. So the 3 principal components are each going to be one of those. And really, I think in understanding PCA, we talk a little bit about this in lecture, I guess a lot actually. What really comes to my mind, or what I think is really helpful when thinking about PCA, is maximizing variance. So that's really the key part about what PCA is trying to do. And the idea is that, okay, so our surfboard is here, and if we want to reduce this to this 3-dimensional data down to maybe 1 or 2 dimensions, we want to preserve as much information in this data as possible. And the way PCA accomplishes this is by choosing the directions in the data that maximize the variance. And so part A asks us to choose the first 3 principal components between length, width, and thickness. And so from just looking at this plot here, it's pretty clear that the points vary most along this kind of length direction here. And if you want to look back at this discussion worksheet, you can imagine that this surfboard is a set of points. The direction along which the data varies the most is this length direction here. And so that is going to be our first principal component. And in thinking about what the second one is going to be, we can apply the same logic. So we want the dimension along which the data varies the second most. We've already chosen this length dimension here, so now we need to choose the direction orthogonal, which is important, the direction orthogonal to the first one along which the data varies the most. And so by looking at this image here, it's pretty clear that if we chose this lengthwise dimension here, or equivalently this lengthwise dimension here along this surfboard, the direction orthogonal to that one, along which the data varies the most, is, if you follow my mouse, kind of this dimension here, which is the width, or equivalently this width here of the surfboard, this horizontal width. And so that is going to be our second principal component. And I know I kind of threw this in, but it is important that the principal component directions are all orthogonal to each other. And that is going to important because it's how we define basically the axes of the coordinate system of a smaller dimension than the original dimension. And so we've chosen length to be our first one, width to be our second, and so we're only left with one more, which is the thickness. And this is pretty clear. We see that like this little thickness here is, also orthogonal to the length and the width. The thickness is orthogonal to them, and it's the direction along which the data varies the third most, I guess, or least in this case, since we only have 3 dimensions. So for part A, PC1 is going to be our length, PC2 is the width, and PC3 is the thickness. And these are all orthogonal to each other, which is important in PCA. Okay, so that covers part A. If you move on to part B, we're asked which of the 3 PCs should be used to create a 2D representation of the surfboard and why. And it asks us to make a sketch, which I have some code below. So, and I think maybe the easiest way to do this is just to kind of talk about it, right? So if you want to make a 2D representation of this 3-dimensional surfboard, well, it kind of makes sense that we should choose the 2 PCs which explain the most variance in this surfboard. And luckily, we kind of already did that in part A. So the 2 PCs that explain the most variance are PC1, the length, and PC2, the width. And so these 2 those 2 principal components should be our choices used when we create a 2D representation of this surfboard. And so in part B, we can imagine, here we have PC1 on this. I'll just run this to show it again. But basically, you can imagine that this ellipse here is this ellipse defined where PC1 is the length and PC2 is the width, lengthwise here, and width being here. This ellipse is what our 2D representation of the surfboard is going to look like. You can kind of imagine if we have this 2D surfboard here and we're interested in the length and the width, we put that into 2D, into 2 dimensions, it's going to look like this ellipse. And importantly, this ellipse is centered at 0, 0, since we always center our original data, as I was saying. And another way to think about choosing principal components in kind of a more general setting is kind of illustrated by this sentence I've written here. So if we have a d-dimensional data set and we want to use PCA to make a representation in k-dimensional space, k is going to be less than d, that's the whole point of using PCA, the principal components we should choose are the first k principal components. And that's exactly what we've done in this example. So we have this 3-dimensional data, and we want, in part B, a 2D representation. And so when we want to make this 2D representation, the first 2 principal components we should choose are exactly what we found to be the first 2 principal components. And that just goes back to the idea of maximizing variance, as we think that will preserve the most information possible. So that's it for parts A and B. Part C is, there's no really code needed for it. We can just simply look at this, or question 2 rather, not part C, gives us this scree plot. And So really what a scree plot is doing, and you'll see this in homework 8, and I know we talked about this a bit in lecture as well, is it's showing us how much variance is explained by each principal component. So there's no x-axis label here. That's bad data science practice, sorry about that, but this should say principal component number. And so, sometimes you'll just have raw variance, which is what we have here. Sometimes you'll have like a fraction of variance explained, and you'll see both types of scree plots in the homework. And so this question 2 says, look at these scree plots and determine for which data set PCA would provide the most informative scatter plot, plotting PC1 and PC2. And so again, we should think back to what we did in part B when we made this 2D representation. A scatter plot is going to be two-dimensional. Maybe I'll give you all just a couple seconds to think about this before I reveal the answer. So again, PCA is about maximizing variance. We want to explain the most variance possible. And in this question, we have 2 data sets, and we want to determine which one could best be represented in a scatter plot after performing PCA. And really the key thing is to look at the y-axis here. So I'll maybe zoom in. Look at the y-axis here. And you'll see that in data set A, these variances are incrementing very slowly, so only by 0.02 units of variance each tick. Whereas here for data set B, these increments are substantially larger. So we're going from 0.5 to 1 to 1.5 to 2 to 2.5. And so, if you look at this data set A, remember we're interested in a two-dimensional scatter plot, plotting PC1 and PC2. So by only using, in data set A, by only using the first 2 principal components, we're really not explaining much variance at all. We're going from, maybe this is like 1.07 here for principal component 1, the variance. Principal component 2 only reduces us to maybe 1.05, and then 3, we only go down to 1. So we can see that the variance is really by all 4, explained by each of the 4 principal components, are all pretty similar. And so just using the first 2 is not going to be very helpful relative to what we see in scree plot for data set B. So here we see that principal component 1 is responsible for 2.5 units of variance. Principal component 2, we see that we explain a lot more variance. We go from 2.5 all the way down to 1, and then we see, kind of a not such a stark decrease, but because of these axes here, a much more substantial decrease for data set B than for data set A. And so data set B, we can explain much more variance with just the first 2 principal components than we can for data set A. And so that's why data set B is after performing PCA and making a scatter plot, the scatter plot for data set B would be much more informative. And that wraps it up for questions 1 and 2 of this PCA section. Please feel free to leave any questions on Piazza if you have them. All right, thank you all for watching.